Okay, so today we're going to talk about two different types of formulas two classifications of formulas, I guess. So we have something that's known as an empirical formula, and then something else that's known as the molecular formula.
Where should we write this down?
Just in your notes where it says topic 1.3, there's just kind of some blank space above the practice problems. You just put these definitions there. Okay, I'm going to give you an example of each, and then I want to see if you can figure out what the difference is. Okay? I'll put these examples down here. Okay, so this is a molecular formula. Whoops, already off to a bad start. Okay, so that's a molecular formula. This is its empirical formula. Evan?
That makes sense. Is this just like a ratio?
Good. Yep, so empirical is just the smallest ratio of a compound. Have a smiley face for that, Evan, by the way. The molecular formula is the total number of everything there. Forgot how far I can write and they still see. I can go pretty far. Okay. Oh, I can't go pretty far. Okay, we're just doing like a very big problem today. So you see me writing outside of the screen.
Just draw like a line on both sides.
That's true. Where's my line? Here?
A little to the right. Right. Yeah.
Right there?
Right there.
Right there? Okay, perfect. That's why you're in AP. Great ideas. Okay, so that's empirical versus molecular. Now, this is the true formula. This is what it actually is. Okay, for example, this is called glucose. Okay, glucose is a form of sugar. We eat this, we use it. This is not glucose. Okay? If you ate this by itself, you die. Okay, it's not good for you. But it has the same ratio. Okay? So for example, once again, some things can have the same of both. So like water. Okay, water's molecular formula is H2O. What would water's empirical formula be? Still just H2O because it can't be simplified further. The only benefit to an empirical formula is it helps us find this later. It's really just a stepping stone. I don't know if it's working. This is B7 though, by the way.
It's B7.
Yeah. You're welcome to stay and listen though. By Zoe. She had me last period. Okay. I lost my train of thought. Empirical, molecular. Okay, this is the real one. This is a stepping stone to get there. So something else that can be done with a mass spectrometer is you can analyze compounds. Okay? All the graphs we looked at last time, like the ones with the bars, those were just pure samples and we divide up their isotopes. You can also throw in a compound like dopamine and find out all the individual components of carbon, hydrogen, oxygen, nitrogen in those ratios. We're not going to look at those types of graphs. We're just going to see the percentages from it and then figure out the formula. So this is literally how, from an unknown, you can figure out what it is. Okay? All right, so let's take a look at this first problem. Oh, ready, set, go. I'm going to use some different colors here in our process to help show the different steps. So if you have different colored pencils or things you want to help note that as well, it could be beneficial for you. If you'd like to borrow colored pencils to label anything. Anyone want to borrow? Anyone else? Good? ground. Okay, so our problem says here, ascorbic acid contains 40.92%, carbon. We lost a carbon on that question. Label that on your notes, everybody. So 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. So I have this sample. I get this data out that it has this much of each of these, okay? Our goal is to find the empirical formula. So circle our goal, empirical formula. Now here's how my problem-solving brain works. I circled what I want, so then my next question says, what's an empirical formula?
That's the ratio.
Good, so we're looking for, our final answer should be C something, H something, O something, right? So keep in mind, this is our end goal. It's always a good idea to know where you're headed in a problem, right? Otherwise you can go sideways and upside down. Okay. Step one for determining an empirical formula is we've got to get out of percentages into something we can measure and work with. So when you're in percentages, step one is we are going to assume that I have 100 grams of my sample. The point of assuming 100 grams is I can change percentages to grams. So I can say, all right, I have 40.92 grams of carbon. I have 4.58 grams of hydrogen and 54.50 grams of oxygen. Step one. Now, once again, thinking of our end goal, what unit are these numbers measured in? Or what are they maybe not measured in? Let's start with the unit of grams. Do these numbers correspond directly to grams? No, right? When you read the formula H2O, it doesn't mean 2 grams of H and 1 gram of O. What does it mean? The number of molecules, right? It's narrowing it down to the individual thing, which is always proportionate to the mole. So the next step I'm going to do in green is we got to convert to moles. We got to take what we have and convert it to moles. Okay? All right, so I'm in grams. Is grams directly connected to moles?
Yes.
Yep, because everything connects to moles, so I can go grams to mole. What's the connecting bridge? Max? Molar mass, so carbon, 12.011 to 1 mole. Plug that into a calculator and we get an answer. Someone shout it out if you get it before I do. 3.4069. Now, we're not thinking about sig figs yet because we're not to the final answer. Okay, when you're doing steps in a problem, just don't even think about sig figs. Just keep decimals. More the better. Okay, round when you get to the end. Okay, good so far? Okay, that's moles of carbon. All right, same thing. Let's find our hydrogen. So 1.008 grams to 1 mole. And then we're going to do the same thing for our oxygen. Side note, if I ever use a marker color that you can't see, especially if you have color blindness or even if it's just bad, let me know so I can get rid of it. Okay, grams of oxygen to 1 mole. And okay. Questions so far? Okay, I'll let you write that out. So there's our step 2 is we converted them all into moles. Now, technically, we kind of have an answer. But the problem is they can't be in decimals. They have to be a whole number, right? Because otherwise that doesn't really make sense to have 3.4 of a carbon atom, right? Because you can't have partial atoms. So to get it to a whole number, step 3 is we are going to divide by the smallest moles. Probably say divide each by the smallest moles. Find ratio. So we're going to divide each by the smallest moles to find our ratio. So in our example, so we're comparing our 3, in this case 3 different moles here. Oxygen is the smallest barely. So I'm going to divide all of these by oxygen's amount. Okay? So divide those through. This one's going to be exactly 1. This one's like 1.00 something. This is 1.33 something. So we divided by the smallest. Now, step 4, you may not have to do. If after you divide by the smallest, these are at whole numbers, you're done. And you just set them up in the formula, there's your answer. If they're not quite whole numbers yet, then we need to think of a factor we can times them by to make it a whole number. Okay, so step 4, make sure you make it a big if. You may not have to do this, right? So if they're not whole numbers, multiply all by common factor. So if they're not at whole numbers yet, then we're going to multiply them all by something to get them there. Yeah, Carly. So that was to get it into the ratio, like what is the ratio of them compared to each other? For every one of these, I'm going to have how many of these? Does that make sense? And then this is because we can't report it, as 1.33 of an atom. So does that make sense? Good question. Oh, you asked a really great question, Carly. They're very grateful over here. Okay, any other questions? Okay. In this case, what would be my best factor to get this to a whole number?
3.
3, yeah. Why'd you pick 3, Taylor?
Because 0.33 is a third of 1.
Yeah, so think in like fraction terms, right? 0.33 is like a third, and so that's why we're going to times them all by 3. So we end up with 3, 4, 3. So then our answer would be C3H4O3. Now, is this ascorbic acid?
No.
Maybe, but we don't know for sure. No is a good answer. What is this? The empirical formula for it, right? So now, next problem is we're going to learn how to take it to the true actual formula, the molecular formula. Side note, I don't know if I said this before, but ascorbic acid is vitamin C, actually. Same thing. So, okay, now, next problem. It is experimentally determined that the molecular weight is 176 AMU. From this, we want to find out the true formula or the full formula for ascorbic acid. Is everyone good if I erase all this? Just do the next thing? Okay. Sometimes I wish I had a magic button that would just erase my board. I guess that's called a smart board. But okay, so someone remind us by raising a hand, what's the relationship between the molecular formula and the empirical formula? How are they connected? Someone raise your hand and remind us of that. Yeah, Carly.
The empirical formula is like the smallest ratio out of the molecular.
Good, I guess I should bring that back. It was C3,
H4.
thank you, O3. So we know that the empirical to the molecular is just a multiple difference, right? It's either double or triple or quadruple. There's some higher multiple of this. So all we have to find is what is that multiple, okay? So to find the molecular ratio, okay, we're going to take the mass they gave us, which is the total mass, okay, so that's always going to be given in the problem because it has to be found experimentally. That's data from the lab. So unless we're doing a lab on it, it's going to be given in the problem. Okay, divided by the empirical mass that we find from what we just determined. Okay, so molecular mass is 176. When I add all this up, so we're going to add up 3 carbons, 4 hydrogens, 3 oxygens, we get 88 point something. That's just molar mass stuff, right? Which, if I divide these two, I get an answer of 2. Good, yep, so then 2 times by the formula. So we get C6H8O6. And that's what ascorbic acid is.
When you're doing that, do you just round to the whole number?
Yeah, good point, Taylor. This has to be a whole number, right?
Well, yeah, and the 88 too. You just round that.
You could, yeah, because I mean, it kind of depends. Like, they might give you more decimals on this, which if they gave you decimals, then keep decimals. But it's a good thing to recognize this has to be a whole number, right? If you divide them and it's like pretty far off a whole number, that's actually probably a good sign that, well, good or bad sign that you did something wrong beforehand, right? So another big like way you can kind of catch yourself too, what if you get an empirical formula that's bigger than the molecular formula they gave you? Is that possible? No, you've done something wrong, right? So that would be a sign of like, okay, I got to go back to my empirical and work through that. So, yeah, Kate.
How did you get 88 from that?
So it's the molar mass. So I added 3 carbons, 4 hydrogens, and 3 oxygens.
Okay. So you don't use the 1 4 on exercise 1.3a because they already give you 3 grams.
So those were the individual grams of like the percentage values, right? We wanted to know like what is its mass per 1 mole of it.
Oh, okay.
Yeah, good connection though. Any other questions so far? Okay, I'm gonna push you into the swimming pool now. Time to swim. Turn the page and try exercise 1.3C with your table buddy. Ready, set, go! So that kind of goes to the idea of like grounded in like equipment, right? So it's just a matter of the equipment can only measure with so much accuracy, and so that's why you just stop. So good observation. Once you have an answer, give me a pencil drop and I'll go and check it. They're not very good, but does anyone need to borrow calculations? Just make Evan do all the typing.
Okay, there we go. That was the answer. Nice.
Hold off on E. There's a little twist that was on my hand.
Wait, can we just did you guys just round them or?
Yeah.
Yes. So,
Good job.
now we still can have 5 minutes.
So that's what we do right here. If you just do 37.45 divided by 35.4.
And that's actually like a good catch, Carly. If you ever get a number that's like, I don't know what to times this by, probably that. Normally, there's really only like 2 main options that you're gonna pull, honestly. It's either gonna be 3, because it's like a 0.3 or a 0.6 type value, or by 2, because it's like right in the middle of 0.5. Outside of that, if it's somewhere awkward in between, it's until you get like yes. Technically, it's close to 0.5, but I probably still check my work on that. Because it's normally like they're normally pretty clear where it's at. It's also another reason not to drop too many decimals. Because if you drop too many, then it'll change the good and
Yeah. Yeah.
We'll learn. Here's the simple rule for now. Yeah, you typically go left to right. So, yeah. There's like, when we learn how to knit, you kind of learn how to knit extra before, but when you go over the knit and stuff, you'll learn like the specifics, but the general rule is left to right.
So is that right?
It is, yeah. Okay, we're looking pretty good.
You guys get weird juices.
Yeah, for this, if you just round up.
Okay. Okay, here's what we're gonna do. We're gonna do a little, we'll call it a game because that makes it sound fun, right? Okay. This is a game I call teacher student. Okay, so what's gonna happen is I'm gonna pair you up with someone that you hopefully don't work with all the time, just to get a different perspective. And then I'm going to assign one of you as a student, and the other is going to act as the teacher. If you have the job as the teacher, what you are going to do is just take really like 2 minutes is all, or less, and just verbally walk through how we just solved this problem again. This is just a really good, I don't know, process to get your brain to kind of wrap around everything that you just did, right? To verbally talk it through to someone else, okay? So we'll go like this. So Claire, turn around. So you go here. They're there. We're gonna get creative here. Because otherwise, I don't want the back row talking to you like always talking.
I know Dr. Taylor.
You wanna talk? I just do that. Let's take come over here for a second. Just do that. That would work. Okay. Ready? You turn around and talk to Bryce. Evan, talk across the aisle to Matt. Oh, this will work. And then Isaac. Okay, to figure out who's the teacher, who's the student, you're gonna play a quick game of rock, paper, scissors, best 2 out of 3. The winner is the teacher. So who's the winner? Okay, so now you are the teacher, he's the student. You're the teacher. Oh, we did that test? Oh.
And you divide it by the least number.
Yeah, you can switch, I guess, if you want.
Yeah, it is so funny. The other one's actually
Okay, has everyone had a chance to teach? I guess so. Technically just one, but if you switch, that's fine. Okay, if as a student you feel like your teacher did a great job teaching you, you can give them a smile.
You get a smile.
Okay, any questions before we take another step? Feeling okay right now? Okay. The next thing we're going to talk about is another way to determine but that's what you just did. Oh, by the way, I think I checked everyone's answers. I walked around the room, but it should have been HFCl3. So, if you got that, by the way, you can have a smiley face as well. So, okay, so we're going to talk about this thing known as a combustion analysis, which is another lab technique used to determine an empirical formula. I wish we had the capabilities to do this. As of right now, we don't have the equipment to do so. So for now, we just have to talk about how to analyze the data that comes from it. Does anyone know in general what is a combustion reaction? Fire. Yep. Okay, combustion is some sort of fire. Explosion if it's in a closed cylinder, right? So all combustion reactions have a similar setup, you could say. Okay? A combustion reaction will have a hydrocarbon, which means a hydrocarbon is some compound with hydrogen and carbon. Hydrocarbon. Now, it could have other things in it. So even like dopamine can be considered a hydrocarbon because it has hydrogen, it has carbon. It also has nitrogen and oxygen. Okay? But it has to have those two. Anyone know a necessary ingredient for fire outside of your fuel source? Oxygen. So all combustions have to have oxygen because you can't burn without fire, right? Okay, so the idea of a combustion analysis is you take your sample you're analyzing and you burn it, okay? The oxygen can flow in through the side here to cause it to burn, okay? In the process of it burning, it causes the compound to break apart. All combustions will break apart into two things, carbon dioxide and water. And then depending on the sample, you might have more than that as well, like nitrogen dioxide or something. But these will always be there because that's part of the hydrocarbon getting split, okay? In this process, it burns and then travels through these tubes and certain components get absorbed and can then be measured. So this section absorbs the water, this section absorbs the carbon dioxide, and then any extra oxygen just flows out the back. The unused oxygen does. Okay? From this data, we can then determine, just like we did before, the empirical formula and then eventually the molecular formula of the substance. The data just looks a little different. So here's an example of a problem dealing with combustion analysis. Okay, so we have an alcohol, which is composed of carbon, hydrogen, oxygen. Side note, by the way, there are like zillions of alcohols in chemistry, right? It's not just like, there's not just what you might be familiar with in terms of like rubbing alcohol or like what people drink. Okay, alcohol is there's a lot of compounds that are classified as alcohols, by the way. So, side note. Okay, so we take a combustion, we have 2.55 grams of our isopropyl, and it produces 5.61 grams of carbon dioxide and 3.61 grams of water. If the molar mass is 60.1 grams per mole, determine the molecular formula. Step 1, circle the goal. What are we trying to find here? All right, very good. Then we're trying to find the molecular formula. What do we always need before we can get to molecular formula? Empirical formula. Okay, that's what your brain should always say. You got to get empirical before you can ever get molecular. So our end goal is the same as before, in that we're trying to find this ratio. Now, our given information is a little different this time. This time we know that we have 0.561 grams of carbon dioxide and 0.306 grams of water. So with combustion analysis, we're already given a gram amount, but it's different in the sense that they're grams of a compound. So with combustion analysis, step 1 is we need to isolate the individual elements from the compounds into moles. So we need to know how many moles of carbon we have, how many moles of hydrogen we have, and how many moles of oxygen we have. Similar to before, just little extra steps here. Okay? So, first step is let's get 2 moles. So I'm going to go from grams of carbon dioxide to moles of carbon dioxide. Molar mass of carbon dioxide is like 44 point something, 02. Anyone plug that in? Are you just taking my number? Somewhere around there. To 1. We're isolating the carbon side of it. So in 1 mole of carbon dioxide, how many carbons do I have?
1.
Good, just 1. Now, I know this does nothing mathematically, but it's still an important step to make sure that you're getting there in terms of what we're trying to find. Okay? All right, plug that in and we'll find our moles of carbon. Anyone plug that in yet? Zero, 1, 2, 7, 4 moles of carbon. Okay. All right, we're going to come to our water now to isolate our hydrogen. So water has a molar mass of like 18.02. 1 mole of water. And then, for every 1 mole of water, I have 2 moles of hydrogen. So I got 0.03396 moles of hydrogen. Now, we need to isolate, what do we have left? Oxygen. The tricky thing with oxygen is it's in both places, right? So we also have some information in the beginning of we know the total mass of our sample, right? 0.255 grams is how much it is altogether. Yeah, Evan?
Couldn't we just take the carbon one, multiply that by 2?
So the other tricky thing with oxygen, as you were saying, is you're like, well, let's just take this to oxygen, that to oxygen. The other tricky thing with oxygen is in the reaction, I erased it, there's oxygen in the hydrocarbon, but then there's also oxygen we're reacting it with, right? And so some of the oxygen here might not be from the actual substance. It could just be from the air. Yeah.
Okay.
Not a bad thought though. That will work, Evan, if it wasn't oxygen.
Okay.
Like if it was something else, then that would totally work.
Okay.
Yeah. No, great thought though. So now what we're going to do is we need to take it away from the total, so we are just isolating the oxygen out. Okay, so it's kind of still isolating, but it's specific here for oxygen. Okay, so we are going to subtract, I don't know if you want to call it part A, it could be step 2. Subtract carbon and hydrogen from total to find oxygen. But before I just subtract those numbers, there is something I have to do conversion-wise. What do I have to do? Isaac?
You have to divide it by the least one.
Ooh, that's going to come, so hold that step. That will come in it.
Does it change into grams?
Yeah, because those are in moles. Our total is in grams, so we got to get these to grams. Okay? So 1 mole of carbon has a mass of 12.011. 1 mole of hydrogen. Okay, plug those in. Questions with what we've done so far? Give me a second to write that. So now I'm going to take my total. I'm going to take 0.255 grams. Once again, if you draw an arrow, that was just given in the problem, and it would always be given because you know how much you're analyzing. And then subtracting 0.1530 and 0.3423. Zero, 6, 7, 7, 6. Now this is where labeling is going to make sure that you don't miss a step. What is this measured in? What of oxygen? Grams of oxygen. So we got to take it to moles. Because once again, here's our end goal, right? We got to know the mole ratio. Okay, so taking this a step. There's 15.999 grams in every 1 mole of oxygen. Uh-oh, I went past my line.
It's a mass.
You're good.
Is it okay still?
Yeah.
If I write the answer below? Okay. Okay, I got 0.004236. Whew, take a breath. We're not done yet. Does that look like an answer?
No, then you have to divide by the small.
Okay, so now we're getting to what Isaac brought up. So now, but we're really close. So now we're literally doing what we just did before, right? So now we're going to divide by the smallest moles. To get our ratio. Okay, which one's the smallest? Oxygen?
So if the happens
0.004236. 0.004236. Okay, so we're taking the moles. I found the smallest one, dividing them each by the smallest. Questions on what I'm doing here? Okay, I'm going to write my answers below so we can see them side by side. So carbon, you got 3?
Well, like 2.922.
Okay. Hydrogen, we get 'kay. Okay, thank you. And then, of course, for oxygen, we're going to get 1 on the dot. So these are both close enough just to take them to the whole number. So that would give me C3H8O. You can put a 1 if you want, yeah.
No.
Are we done?
No.
Wait, yes.
No, oh, we have to determine the molecular formula.
Yeah,
What's this?
Empirical.
That's the empirical. I know, AP questions do it. You feel like you're there and then you're not there yet. Okay, so this is our empirical.
How do you just use the line card?
Should I have given you more space? We're really close. It's just that little...
Half of a page I thought would be enough.
Yeah, I once in college did a problem on like a poster board. I just kept running out of room.
Oh my god.
Don't worry, we won't.
I'm
That
not going.
one page should be sufficient. Okay, what's my next step? How do I get to molecular?
You have, wait, I totally forgot.
You just, wait, do you have to convert that to grams again?
Nope, we don't have to do any conversions.
If she had said yes, I swear I would have.
So just think of what's the connection between the empirical and the molecular. How are they connected? It's just another ratio, right?
You have to take the weight.
Okay, so we know the molecular mass, right? Here's the formula again.
Okay. And then we have to add a little bit of.
Yeah, whatever mass is
Carbon.
Okay, so molecular mass divided by empirical mass.
36.
You just get 88. Just get the 88.
So the top number, once again, is always given. Okay, that's always given in the problem. Someone get an answer for our bottom one?
I think it's, wait, 53-ish. I did that in my head, so I don't know if that's even close.
Shout it out when you get it. There's a reason I'm not telling it to you.
Just one.
So what'd you get for the empirical mass, Taylor?
The empirical mass, 60.085.
So it's the same thing.
So we actually did have our answer.
Yeah.
We just didn't know it was our answer. Because if the empirical mass is equal to the molecular mass, the ratio is a 1, right? But we didn't know that, so that's why we had to check it. Okay, questions?
Do we have very many problems like this?
Do you have very many of these on the homework? Not too many.
Not too many, that's too
Not too many. Well, okay, actually of the combustion, I think I only gave you like one combustion analysis. The other ones are like the first one, yeah. Okay, I want you to pair up with your partner you were with before and switch roles. And teach this. Okay? All right, ready, set, go.
So
So basically, you have to separate C's from CO2. And so, to do that, you subtract so basically you have to convert CO2 make that green, add it with the H, and subtract it to mass, and that is divided by, and then you just yes, and then divide by the smallest mole earlier, and then after that, here, and then you have to add your half of the